Okay, this is Newton's law of cooling, which is found to start at the beginning. The beginning of it is at the bottom of page 354. So get there first so you can follow along with it.
3 what?
5, 4. He said 3 what? And I said 5, 4.
Newton's law of cooling.
Ready? 354. This is only slightly different than what we did yesterday with regular exponential, but it's an important difference. You need to pay attention to it. Okay? We're going to solve a differential equation again. Remember yesterday we said dy dt, and then or dy dx, and we separated the variables, we integrated both sides separately. Do you recall that?
Yep.
Gavin's shaking his head, or nodding his head really, really well, because he sat in here yesterday in math lab and did all of those. Who knows exactly what I'm talking about? The rest of you, if you haven't tackled it yet, maybe don't.
Wait, what? 6.
About a differential equation, how you separate it, integrate both sides.
Yeah.
6, 4.
I
6, 4. Okay. I'm just saying, we're going to do the same thing, only with a different scenario. It's all cool. And there's a subtle difference, but it's a really important difference. So listen. I'm going to read to you on page 354 at the bottom. Soup left in a cup cools to the temperature of the surrounding air. Duh, right? Everybody has experienced that. A hot silver ingot immersed in water cools to the temperature of the surrounding water. In situations like these, the rate at which an object's temperature is changing at any given time, and here's the key, is roughly proportional to the difference. That's how it's different from what we did before, is the difference between the temperature that it has right now and the temperature of the surrounding medium. It's the difference between the two. I mean, difference in math means what?
Minus.
So, this is what we have. Yesterday, just to show you how the two compare, if we were talking about money yesterday, we said that the rate at which the money is changing per time is equal to the amount that we have right now times some k value. Do you remember that? Were you convinced that was reasonable?
Yeah.
Well, now, based on the words that they just wrote for us there, we're talking about temperature, they're saying that the rate at which temperature is changing with respect to time, notice the capital T and the little t, they're important, is equal to K times the difference between the temperature and the surrounding medium. We're going to call it TE. He calls it TS for surrounding. I call it TE for environmental temperature. Okay? So, I don't actually have this correct yet. I've got the difference over here, but I don't have the difference over here. How can I change this so that it represents the difference in the temperature? Because it said it's proportional, the change in the temperature, okay, let me read that again. The rate at which the object's temperature is changing at any given time is roughly, oh, you know what? I did read it right. Okay, let's write it. This is correct. Let me tell you why. Hang on a second. I thought it was incorrect. It's not. It says, the rate at which the object's temperature is changing. That's dt. That's the rate at which the temperature is changing. Is, there's my verb, equal sign, proportional to the difference between the temperature now, right at this instant, and the temperature of the surrounding medium. Proportional means K times whatever comes after the word proportional. And it's proportional to the difference. This is the temperature at any given instant of time, minus the environmental temperature it's trying to cool down to. That difference is proportional to the rate at which it's changing. Yes?
Why do they have a negative K?
Because, yeah, I probably should too. It's going to be a negative number now. It's going to come out to be negative anyway. Because something is hot, is coming down to the environmental temperature. If it were something that were warming up, like if you took something out of the freezer and set it on the counter instead, then K would be positive because the temperature is increasing. So the sign on K is all about whether you have a decay or a growth.
What is K?
Again, it's a constant which is related to the type of substance which is cooling. K will be different for metal than it will for milk, than it will be for hot chocolate. Very slightly different because of the sugar.
Will the K change automatically depending on whether it's cooling
K will take on the correct sign automatically. So I'm just gonna leave K here, and it will be positive or negative depending on whether it's a growth or decay, whether something's cooling off or warming up. The same rules apply. You with me? They use this formula, well, not this one, I have to get it solved, you'll see it. They use this formula when they're trying to detect how long someone's been dead.
Way over the liver.
By taking a probe. It's just like a meat thermometer.
They just
And
have to have
the person's dead, and the thermometer is kind of dull at the end, quite often. Doesn't matter, they're dead. They stick it in their liver and wait for the temperature to quit changing, and that's their internal body temperature compared to the surrounding temperature, and they can tell how long the person's been dead by finding this.
Well, I've got to be.
I can tell just by
This person's been dead for.
One thing, and I've seen this on CSI a couple times, they got the time of death wrong, and the criminal was a little smarter than most. They get the time of death wrong because they get the surrounding air temperature to be different when the crime people show up than it was when they were killed. Now they've got something, and if they don't know that, if they think it's a constant all the time, they get the wrong time of death.
those knuckleheads.
That's
Yeah,
pretty
they-
smart.
Yeah. There's ways to beat the system. You know how we say criminals are so dumb? Only the dumb ones get caught.
Only the dumb ones here.
Smart ones, we don't ever say criminals are smart because we don't talk about the things, the crimes that are gotten away with. We talk about the ones that are solved.
Yeah.
Just saying. All right,
No, they have yet to find these.
Take it more.
all right, so guys, ladies, this is a differential equation. We need to solve it. That means we need to find capital T equals something with a little t in it. Remember yesterday we were solving that one for y equals something with a t or an x in it, remember? We gotta solve this. First thing we gotta do is separate the variables. How do we do that?
We pull the t's over, and we pull the difference of t's over with the.
So we take the dt, leave it on the left, and bring these guys over. Yeah, by division, because it's a factor,
K.
equals k dt, little t.
Yes.
Yeah?
Yes.
Then we,
You're right. No.
other one,
Integrate.
integrate. Because we got, so this is dt, and we're gonna integrate this, and we're gonna integrate this to recover, to try to get at what t is. Because this is a derivative, we want to anti-derive using an integral to recover what t is, not dt.
Could we separate the dt over t minus the integral of dt over t?
That's a nice thought, but no. That doesn't, listen, shh, listen. Let me answer this question first. Shh. When you have a monomial, a single term in the denominator, you can put it under each separate term this way. But you cannot do the same thing with a numerator. That doesn't apply.
That makes sense.
It happens to a lot, a lot of people think you can, but it doesn't apply that direction. So we can't do that. This thing right here, even though it's a difference, listen, it's a linear difference. What do I mean by linear? This thing's constantly changing, so this is a variable. This is a constant number, right? That's like saying x minus 4. Can you see that that's linear? This is also linear. And if you have a linear denominator, only if you have a linear denominator, can you use a logarithm to antiderive? We can, because it's linear. So the antiderivative of this is the natural log of t minus te. Now,
Well, why?
One over something.
Yeah.
Chain rule though?
Yeah, that's what I was.
you don't need a chain rule
Why?
because it's linear.
Derive that now.
Yeah, got it.
Are you sure?
Yeah.
You can just, if it's linear, you can just log it.
Yeah.
Oh, wait. Oh, I understand what you're saying. Yes, if this were a 4x minus
Then it'd
2,
be like,
then it would be the natural log of 4x minus 2.
4.
4?
No.
1/4.
4.
Wait, what?
You're anti-deriving.
Anti-deriving, yeah, got it.
But since there's a 1 in front of here, that doesn't apply here. But that was a good thought. But it doesn't apply here. If you just got an x here, just a single variable with a 1 for a coefficient, then you don't need to fix this with the chain,
So are
okay?
they both variables?
That's a good thought.
Or is it t the variable and then minus t kind of a constant?
T is a constant.
Equals kt.
For what we're doing right now, we're cooling something off. Something's hot, we pull it out of the oven, we turn the unit off, something like that. It's cooling down. Will this difference be positive all the time?
Well, it's
Yeah.
absolute value.
It will be, so I don't need to do that. I don't need to consider that for right now. Okay? Everybody clear?
Yeah.
Okay, so that's that one's integral, and I'm not gonna put plus C over here, because remember, we like to keep this side as pristine as possible, we're gonna dump all the C's over there. What's this one's integral?
One little t.
K little t plus C. Okay, everybody okay with the integral? Since we don't have an initial condition, right here is where we plug that in to find C. We don't have one, we're just gonna keep the C. Remember, we're after this right here. What do we do next? E it. Good phrasing. So that if I E this size, it's gonna be E to the KT plus C equals T minus TE. Did y'all follow that? We eat it. Okay, so we got one more, well, wait. I'm gonna come up to here so that everyone can see. I think I'm still, yeah, we're good here. Okay, so I'm gonna turn it around because I'm used to seeing this on the left. TE equals, and at the same time, just like I did yesterday, I'm gonna say that's E to the KT times E to the C,
Which is a constant.
which is a constant. And so T minus TE is equal to A, E to the KT, right? And I'm just about done solving for T, and I could do it by just kicking TE over here, but before I do that, we have to really think about what was going on, especially starting right here. We're not gonna leave that thing as A. Do you remember what we changed A to yesterday when we solved this? Do you remember the solution to this? Can anybody tell me without doing it all through? Y equals,
Why not?
why not E to the KT? Is that what it turned out to
We just
be?
changed it to why not?
No, we changed to.
So we changed this to
It's not T
T
naught.
naught?
No, because it's our final thing.
T naught. It involves T naught.
beginning. That's the
Is it
Why not the initial?
the little t?
No, because that's our very.
Different.
Can anybody tell me in words what this said? You can read it out of the book if you
That's
want. Maybe it'll remind you what we're doing here.
if T is the temperature of the object at time T and T is the wait.
Go to the bottom of the page.
Difference of the difference between its temperature and the temperature of its surrounding medium. The starting temperature.
It's proportional to what?
Oh, so A would have to do, A has to do with the conductiveness of the.
Nice try. Oh, I thought you had it. No. It's all about this right here. It's proportional to what? The difference in temperature. So that A has to be the initial difference.
I already said that.
Well, speak up. I didn't hear you. You know, I'm going deaf. Well, I already am.
Initial difference, what do you mean?
The initial difference in the temperature. So this is the initial difference in the temperature, which is this.
T naught minus.
So
That's the initial
what's
difference.
just plain T, what's plain T stand for?
The temperature of the object.
Oh,
So you're trying to solve for t.
wait, but
And
what's
what's
T
T
out also the temperature?
And then
of
you
the object?
add the TE to the other side and it cancels
People,
out.
this particular T with no subscript is the temperature of the object at any given moment in time. So this is constantly changing.
Okay, so that's technically T to the T.
This is the difference in the temperature at any given moment. This is the initial difference in the temperature, just like why not is the initial
The difference
value.
between a thing that you pull out of the oven and everything
So,
else.
so if we're saying that the rate at which it's changing is proportional to a difference, then this has to be the initial difference.
Yeah.
Y'all follow?
Yes.
Just like why not over there was the initial amount, this is the initial difference if this is any difference as time rolls along. Y'all see it? Now, I would kick the TE over, but I'm not gonna, because I want you to see the relationship between these two as we use the formula. So I'm gonna circle this. This is the solution to that differential equation. And this is the environmental temperature, it's used twice. This is the temperature, which is constantly changing at different rates.
That's a variable.
And this is the environmental temperature, oh, sorry, this is the initial temperature when we start the clock, when T is 0. This is the initial temperature. This is time. These are all temperatures. So it's important that you use capital and lowercase letters appropriately. Now, let's try a problem. This one isn't too bad. Listen carefully and have your calculators handy. Here's the scenario. A hard-boiled egg at 98 degrees Celsius. Why wouldn't it be 100 degrees Celsius?
But it's 98. Because you don't want to boil it.
It's
you could boil it.
Okay,
It's
yeah.
just you're above sea level a little ways.
Yeah. Because there's less atmospheric pressure, it takes less heat for the.
Whoa, okay.
It takes a smaller temperature to get the water to boil.
So
Did
can
you know
boil
that you
it?
cannot hard boil an egg in Tibet?
Why? There's not enough atmospheric pressure.
You can only, listen, the coagulation temperature of egg white is around 79 degrees Celsius. Boiling water without a pressure cooker in Tibet will get up to about 76 before it begins to boil. Because there's not enough atmospheric pressure to keep the bubbles from coming up. Because you're so hot.
Oh, so it won't actually heat the egg.
Right, it won't get hot enough to coagulate the egg white.
That's actually.
That's why you.
It is cold.
Yeah,
You want a hard boiled egg in Tibet, you're gonna have to have a pressure cooker.
Could you boil it in something that takes more heat to boil?
Oil?
Yes,
Put you what?
Mike?
Higher than
Oil.
Oil.
something heavier than water,
Heavy water.
Hey, big
might
water.
be dense enough to actually crack the egg. It's going, maybe, you might could,
Thick water. Thick water.
thick water.
Iron.
What is it? Is
Mercury.
the water, it's got like an extra hydrogen.
What's really, really strange is to see a tub of mercury and have somebody put a ball bearing in it, floats.
For real?
Yeah.
Weird.
My favorite is
Steel is way less dense than
Have you watched that?
sulfur
Yeah.
hexafluoride.
you probably Google it, don't do it now, don't touch your phone. All right, we're gonna solve example 6, okay, so it's 98, probably because there's 1,000 or 1,500 feet elevation, okay? Anyway, it's 98 degrees. Put in a pan under running 18 degrees Celsius water to cool. Why is it important the water is running?
That way the
Otherwise,
water
it's
pressure
not
doesn't change.
Yeah, otherwise your surrounding medium begins to change, and now you've got a double integral to solve because you got two things changing.
Wait, oh my gosh, that'd be kind of.
And then you have to.
So we're gonna let the water run and it maintains 18 degrees.
Are we gonna do one of those?
No, not in this class. You will later.
Shh. My bad.
Shh. Then it says, after 5 minutes, the egg's temperature is found to be 38. Question we have to answer is, how much longer will it take the egg to reach 20? Eventually, when we're done with this problem, we need little t. But for right now, we have little t and we must find k for this situation.
And then fine.
Okay, so here we go. Let's see if we can fill in the gaps. I'm going to erase the solution. The solution's in your book. Well, it's not very well written. I wrote it. I crossed mine out and said, here's an alternative, which is what I did here. Okay, because it resembles this a lot more than what he did. All right, so we're going to take this formula. It's the only part I'm not going to erase, so I've got it here, and I can continue to show Sonny what we're doing. And we're going to use that formula and try to solve this equation. So we begin filling in things. What is the temperature of the egg right now?
38.
No.
38.
38.
Oh, 38. This temperature, yeah.
What is the surrounding medium?
18.
18. Equals, what is the initial temperature?
Was
98.
98
minus 8.
minus 18.
E to the K fifth.
E to the k times 5. Do y'all understand all those details we got from the words and where we put them? Because that leaves us with this equation with only k to solve for. That's called a snapshot of data. You take that snapshot of data and it leaves you only k to find, and then we will use k to get at the rest of it. What?
So 18 is the medium temperature?
It's the surrounding medium.
Oh.
The environmental
Thing that you're.
The environmental, whatever it is it's cooling in, that's its temperature. Everybody clear? So far on the substitutions?
Yeah.
Now we go after k by first figuring out these two constants. This is 20 over
I can check that too.
Oh, 20 over 70.
over 70. Can I do this?
Yeah.
Can we just put a natural log on that right now?
Sure. If everybody's
Or would
following.
it be 80?
Equals K5.
Yeah, wouldn't it
Oh, yeah, 80.
Yeah, it'd be 80. Dang it, Sam.
Is it 80?
Let's just straight.
Whoa.
So be one word.
That threw me off.
Okay, now we're okay?
Yeah.
I wasn't doing the arithmetic at all. I was trusting you guys.
My bad.
No, it's okay. All right, we got that so far?
Sam,
Did everybody get from there to there and do all that math in your head?
Yeah.
So it's the natural log of, and I'm going to use a decimal so it's easier to put in my calculator when it comes time, over 5. That is k for this situation. Are we clear?
Yeah.
Now we're going to go find little t. Well, we have to be careful about the words, and you have to read it really carefully what they're saying. It does not say how long does it take it to reach a temperature of something. It says how much longer. So here's the deal. To reach 20. We're trying to figure out how much time it takes to reach 20 now that we know what K is. So here's the situation you've got to think about. You can find it directly if you do it as though the initial temperature were 38, trying to cool to 20. That would tell you how much longer. Because we've already gotten to the 38. We already used up 5 minutes getting to 38. So if we start the clock again and wait for it to cool to 20, that's much longer. Or we can use the exact same numbers, and when we find the time it takes to cool to 20, we can subtract the first 5 minutes. Because it's asking how much longer, not how long will it take from initial. So my question to you is, do you want to use 38 as the initial and find t directly, or do you want to find it using this data and subtract 5? Because it doesn't matter. You want to go with the 38?
Sounds cooler.
However you do it, you have to understand what you're looking for and how to apply the initial things. So it won't be this anymore. We're going to use this again. Only this time we know what K is. So what's the temperature right now?
38.
I mean, what's the temperature we want to figure out how much time?
20.
20. 20 minus 18 equals. This is where the 38 comes in.
Minus 18.
Okay.
Temperature.
E to the, that
E to the
number, which
E
is
to the
negative 0.277.
log of a quarter. I don't want to put that in there because that's an estimation. I'm going to leave this until I finally calculate. That way I don't have to risk a approximation error. By the way, these K values on all these exponents are extremely sensitive to change. You change them a little bit, you change the answer you're looking for a lot bit. So I would use them in their unapproximatedness if at all possible until you're ready to calculate. So the only variable we have now is t because we found K using that snapshot. Okay? So I get what over here? Just a minute. 2 over what?
2 over 2, which is 110.
Natural log of that is equal to the natural log of a quarter over 5t.
And then we divide that out.
So it's the natural log of a tenth, which I'm going to call 0.1, over this. The natural log of, we could put a 5 up here if you want, but whatever, we can invert multiply, but I'm not going to. 0.25 over 5, and that's how much longer it will take when you use the 38 there.
8.3.
8.3 what?
Minutes.
Minutes. This is really good evidence that this thing is exponential and dropping faster at first.
Yeah.
And it's beginning to flatten out because it took 5 minutes to go from 98 to 38. It took another 8 minutes to go from 38 to 20. Lot smaller gap in temperature, a lot more time because it's starting to flatten. Okay, we all right on that? Now let's see if we really understand what's going on.
The temperature at that moment.
I'm going to show you something about your calculators that you may not be aware of, or maybe you are, but I've forgotten. I don't know.
It's going down.
Once again, if you'd like to go out, if this is the distraction, you can. Okay. My students are very, very adept at ignoring me. They're not so adept at math, but they're really good at it.
This is kind of uneasy to ignore because it's like, way high.
Right.
Oh yeah, this is like.
Okay.
It's like listening to
All right.
Wasn't there a class there about cooling a few weeks ago?
Doing what? Exponentials, yeah.
Yeah.
But not like, I mean, the only thing that's calculus here is the differentials. They've done something. Maybe not with Newton's law of cooling, but she's familiar with that stuff. We gotta quit talking about it because she's gotta concentrate. So. All right. Example 7 is more like real life when you have to use this, but it's also more difficult. So pay attention here. It says a temperature probe, which is a thermometer. Possibly. But we're not doing a dead body, we're just doing water. Doing a cup of coffee. Listen. Shh. Temperature probe or thermometer is removed from a cup of coffee and placed in water that has a temperature of 4.5 degrees Celsius. And for your information, that temperature in that water that we put it in is not going to change, so get over it. Shh. Temperature readings T, capital T, are recorded in table 6.1, and they are taken after 2 seconds, 5 seconds, and every 5 seconds thereafter. Why not 0 and 5? Because it took a second or two to get that probe out of the cup and put in the water. The clock started when we took it out of the cup of coffee. 2 seconds later, it was immersed in the cooling. You see what I'm saying?
So we don't wanna use those first
No,
two
I lied.
seconds.
I lied, that's not true. It was put in the water and somebody was late starting the clock.
Oh,
So the first temperature reading taken after it was put in the water was 2 seconds after it was placed in the water.
okay.
All right, and there was 5 seconds, every 5 seconds in intervals after that. These are our two things that we have to handle. The coffee's temperature at the time the temperature probe was removed. So we want to know what the actual coffee's temperature was when this whole thing started. And the time when the temperature probe reading will be 8 degrees. So we want to know the initial temperature. And we want to know how long it takes to get to 8 degrees.
So would T naught be the temperature of it when it was, are we assuming that it was?
When time was 0, it's T naught.
Okay, but that was when it was placed in the water, kind of like.
So here's what happened, okay? Cup of coffee here, water here. Water's at 4.5, it's gonna stay that way. Here's what the guy did. The guy was supposed to run the experiment. I mean, a couple of kids in the chem lab, you know. They took the probe out, they put it in there, and then he said, oh crap, we need that temperature. 2 seconds later, and he read the first one 2 seconds after he put it in the water. So we don't know what the initial temperature was because it had been cooling for 2 seconds. Do you understand now?
So we're not taking into account though how much you cooled while it was in the air.
No, we're not.
This is the reason we just.
The time that we're looking, when we're assuming that it maintained the same temperature long enough to get into the water. And then the guy started to walk away and said, nuts, we need that. And he put that down as 2 seconds because the clock had already started.
I would have just taken it out and put it back.
I know, but that's not what we're doing. I would have too. All right, so here's our formula, folks, right here. K has to be negative. It'll come out negative on its own. Because look at what our K was. K over here was a negative. Look at it. A negative divided by a positive, right? So it comes out negative on its own. You don't need to worry about that. But it is a negative number if it's cooling, which is happening here. Okay, so we have to use the data. What kind of a function is this, by the way? Exponential.
Okay.
And we're going to have to figure this out by doing a plot of data.
Can we just do from one set of data points to one more, like from 10 to 15, and then plug it in, and then find a K value?
Only if we have an initial one to put in for this, which we don't.
Isn't that what we're finding?
Wait, but we don't need that. Because we have everything else.
You don't have K.
Yeah, you would. You could treat the temperature at 10 like the initial value to get a K value.
All right, you proceed with that, and we'll proceed with calculus.
Like,
I'm not saying you're wrong.
how is that not? I mean, it works.
I'm not saying you're wrong. Go ahead, you do that. See if it works out. That's fine. I'm not shooting you. I'm not shooting you down. I'm showing you how to make your calculator work in the situation.
All right, that's good.
All right, listen up. What we're going to do is in your stat editor, put the first 2 columns in there. These are actual values. That one was on the clock and one was on the temperature probe. So put those values in your list 1 and list 2.
Which 2 columns are we putting in? The first
The
two?
first 2. I think that's me.
Sorry.
5, 6, 7. Okay.
First.
Okay. Why would the author give us the third column and don't enter that?
Just to make it a little easier, it's only 4.5 off.
Well, that gives us.
Why would that be important though in this problem?
That gives us what we put on the left side of the equation.
Yeah, it gives us this as a single number instead of something that has to be subtracted for everyone. Now, here's how you make your calculator good. Just for your information in the future, if we go up and highlight list 3, so get list 3 blackened, the actual word or the actual thing, L3, and now we can define it. And I want to define it to be list 2, so I'm going to go second and the number 2, minus 4.5. That's what I wanna do to every number, right?
Wait. Let's do.
Oh,
That is cool.
Isn't that pretty cool?
Okay.
Oh, wow.
It takes every element and subtracts 4.5 immediately and fills list 3 with it because that's how you're defining list 3. So, for instance, if you had a whole bunch of widths and a whole bunch of lengths for
That
rectangles,
makes sense.
you could put them in list 1 and list 2 and have it calculate the area by defining list 3 to be list 1 times list 2. And find them all immediately, which is cool.
How do you get?
So I wanted to show you that aspect about your calculator, but you have to be highlighting the list that you wish to populate, and then you have to tell it how you want to populate. You see what I'm saying? Okay, now, we want to do time versus this difference and get a plot, which means we want time list 1 versus list 3. Because this is like y and this is like x. I want this versus this in a plot. I want to plot the point, little t, comma, this difference, which means I need list 1 and list 3 to plot. You with me? That means we got to change the stat plot, or at least go to plot 2. We got to go look at things. So I want you to go second and y equals. Second and y equals gives you that, like this. And we have to either redefine plot 1, or we have to look at plot 2 and see if it does list 1 or list 3. Mine doesn't.
Mine does.
If yours does list 1 or list 3 already for plot 2, then just turn on plot 2. I'm going to change my plot 1. So I'm going to hit enter on plot 1. And I'm going to go and change the y list to L3 by hitting second and the number 3.
So you only want that plot 2 on?
Only the plot 2.
You want list 1, list 3.
Right. Yeah, I don't want 2 to come into it. 2 was only there to define this. Okay. Now, go and turn on whichever plot you defined to use list 1 and list 3 in. Whatever that was, go turn it on. Oh wait, let's find a window. And by the way, clear out any equations that are in there. What window shall we use for this?
I did
Find out 2 minus.
0 to 45 and 0 to 70.
Okay, that would be really good, except for I want to know where it crosses the y-axis. So I'm going to go slightly before that with my x's. I'm going to go from -5 to 50. So that I can see my x-axis where it's going to cross, because that would be my initial temperature, right? I want to be able to see it. Okay, 5, probably 10s, and then the y's are going to go from the smallest one, 7.5. So I'm going to go, the 0's fine on that one. 0 up to, I'm not going to get much harder than 60, so I'll go to 7 by 10s. Okay, now go turn that plot on, the one that you designed, and see if you can see the points, and see if it doesn't look like a decaying exponential. Were you able to see it?
Yep.
Everybody got it? Good,
What
cool,
plot do we turn on?
cool.
We turn on L2.
Yeah.
Okay.
All right, now go fit an exponential curve through there. So stat, calc, exp, which is 0, list 1. Don't forget, it's list 3.
Oh, what's our R value on that?
Oh, probably not great.
It's awful.
List 2, comma, bars, y bars, function, y1. It's not bad. R squared is 0.96.
That's a J.
I got 0.97.
Yeah.
Go back, let's just start over.
Why doesn't this?
Let me turn it.
Graph it and see if it looks like a reasonable fit. It's not great, right? It doesn't have the belly in it, it should, but it's done the best that it can.
Tell you what it is. That diagnostics, right?
Did you get that?
Yeah.
What are we supposed to do?
The equation's supposed to be 63.23
Yeah.
times 0.941 raised to the x.
I don't know what I did, but okay.
So if
We're
we
using
do
the
it
L
in list,
Jose, I did.
List 1 and list 3 should be what you're using to make to draw the curve.
I don't know what I did. I don't know. I just found that out too. There it is.
Yeah, we did. Yep, and I'm working on the key.
Not a problem.
Okay, all right.
I couldn't remember.
Okay, all righty, thank you.
I don't know.
Did we get that? Did I get the same thing they did? Oh, no, I got it.
I used L3 version.
I got 61 points, no, I got
What's your,
63.
I got 61.65.
Oh, I know what happened. Ooh, this is gonna get ugly.
That's what I was wondering. Because theirs looks like it's a lot better than mine.
Yeah,
Are you supposed to use L2 or L3?
I think we're supposed to use list 1 and list 2 at first and then account for it. Account for what we did.
We just Google. I got what they got.
No, I lied.
Yeah,
No, it should have been list 1 and list 3.
Oh,
So,
we didn't.
but I got 63 point something.
Miss J, when we calculated, we probably did this one, this two.
No, I didn't. I did list 1, list 3.
Oh, you did?
Yep.
I did, but I got the same.
Nope, I didn't. I intended to.
Okay, yeah, that's how they got the .97.
Yeah.
All
Yeah, you're right.
that
There is a better fit. Sorry about that. Okay, now Mariah, now look at it. Ouch. I intended, I said list 3.
So
And I
you
intended to type list 3.
List 1 and list 3.
So is this what your graph looks like, and your R squared is 0.97? And the value of it is, the equation is 61.65555 times 0.927 raised to the x.
Yeah.
Does that sound better?
Yeah.
Oh, my fault.
So
we were plotting, okay. We were plotting one, but we were getting compared to the other.
In what?
Okay. Can we, okay, first thing we do, we graph all this, and then you guys get a second white.
Yeah.
And then what you do with the plot. Well, 10 is the white. So, what point are you talking about?
Yeah, that's correct. Okay, that's correct.
That, so
What?
check
Did
out
I write down the R?
this one.
Watch it.
So
Catalog.
this one, I struck it. Oh, second grade was. Something else you want, right? You didn't plug in.
Okay, so this is what we got. This is what, take a look what they have in the solution. They have t minus 4.5 because that was our y value, right? Capital T minus 4.5 is our y, and we got 61.66 times 0.9277 to the t. How come? Because, folks, your calculator uses this. Y equals a b to the x for its parent function, and that's not what we want. We've got e's in ours, they got b's in theirs. How are we going to fix that? Because you don't have an exponential regression that uses e's. You only have this. And it gave us a really great curve with a good fit. How can we fix it so that it's correct?
Divided by E. Can we make it using E?
Could we solve?
Is it necessary to answer the question for it to be in E form is what I'm saying?
Multiplied by
I guess.
The question says, what's the coffee's temperature at the time the temperature probe was removed? In other words, what is the initial temperature? That's what we're asking. How can we find that? Maybe we could look at the graph. Remember that this is T minus 4.5, what we have here. That's what we fit into this. And it was A, which was 60 what? 61.66 555 times, what was it?
Point something.
Like that?
927.
Like that? Okay?
Good.
Raised to the x is what the calculator gave us. Now, according to what we've got here, these are our y values, and this thingy right here is T naught minus TE. And TE is 4.5, so we can find T naught by
Simple math.
yeah, then
I'm not sure. I think I'm kind of lost.
We just add.
the initial temperature, I'm sorry, the surrounding temperature is 4.5. This thing that we got, this A right here is this thingy right here. It's that voltage at the beginning amount, which is our initial temperature, but it's not the initial temperature. This is the initial difference in the temperature.
So
Knowing that, can we find this?
add 4.5.
Add 4.5?
Wouldn't the natural log of B be
66 ish.
66.5? So could we just do that?
Possibly, but I don't wanna go there. I wanna see if we can answer this with what we got. Do you understand how we can find the initial temperature now that we know this thingy?
That is
66 points.
the actual,
1555.
yeah, 66.
Plus
point
4.5,
5.
which is 66.16. Is that correct? Y'all see how we got that?
Because that number
Is that where it crosses the x-axis, or could you find it on the graph? Could you say, second calc a value at 0? Oh crap, it says 61, why come?
Because we use the ones that are
Because it
shifted
just
down.
told us this.
Yeah.
Still have to add 4.5 to it to get the initial temperature. Do you see what I'm saying so far? Now the second question says, how long does it take for the temperature probe reading to be 8? The temperature probe reading to be 8.
Temperature probe.
Intersection. Ah, I like his theory.
Calculate.
What?
Y equals 8 and find the intersection.
Or just see what.
Do we want to do y equals 8?
12.5.
Which one?
X equals 8.
Thank you.
What equals 8?
It depends on which list.
Axel? What'd you say equals 8? Okay.
We've got, no, we do.
No, because that's a time.
We do 12.5 when we.
I don't know.
Time for the temperature.
I'm saying 8.
I mean, yeah, it'd be 3.5.
You're saying 8 because it says 8 the problem, but what is 8?
It's 3.5. 8 is the temperature.
It is not.
I'm talking to Axel. Jose, turn around, quit staring at him. Put your knees forward. Thank you. Axel, what is 8? What do you think is 8 in this thing? I agree, that's what it's measured in. Look at what we've got up here. We're trying to figure out little t, well, that's little t here, this is a mess here, but we'll put that 8 in here to try to figure out how long it took to get there. Is 8 minutes? You just told me what it was.
Big.
Yeah, big T.
Yeah, this is the temperature. Listen, this is the temperature that keeps changing and changing and changing. We want to know exactly when it hits 8.
So 3.5. X equals 3.5.
That's what I'm thinking. You guys were all saying 12, but I think we want to subtract. Don't you think?
47.
So now let's go with Gavin's idea. Gavin, what did you want to do?
I have no clue.
You did too. And he said, that's a great idea. And I said,
Graph it.
is it?
Well, I don't know.
Gavin, what did you want to do to find this value?
Y equals 8, find an intersection.
Good, but now we want to let it be y equals.
8.
Do we want to let it be 3.5?
Yes. Yeah.
Try it. See.
Wait,
Just try it. Just try it. Go to your y equals screen, let it be 3.5, and let's see what happens.
47. What was your Wait, X equals
After about 38 minutes.
Hold up, wait,
How do you do that?
two.
How are we supposed to find
Oh,
it? I'm not
Can
getting
we just do the original one, we do this one and this 2, and then find go to 8 then? That'd be easier.
Okay, look.
Yeah, I can't.
Let me get you all back in the same place for a second. Are you listening? Remember this whole thing that we've been working with today so far with Newton's law of cooling, is it's the difference between the temperature it has now and the surrounding medium it's cooling. It's the difference that is the y value. That's where we got the 3.5. That's what this graph is dealing with. As a y value is this difference. So we want to graph this y value when this piece of it is 8. So we graphed 3.5 and we got it to cross our graph, which is also dependent upon this difference, to be what? How much time?
38.22.
Okay. And look at what they have in the book. Oh, voila. There it is. Yep.
So this Newton's law of cooling thing
Subtract by 4.
isn't dependent only on what the temperature we want to find, but also on the difference between that temperature.
It's more dependent on the difference.
Right.
Yeah.
Okay, I can accept that.
Yeah. You can?
Yeah.
This is why Newton's law of cooling is more difficult to deal with than just the y equals kt. Well, dy dx equals kt. Remember that we worked yesterday? It's the difference. And the difference by itself is a single notion, yet it still has to be figured with 2 numbers. That's what makes it hard.
Oh, so it's basically the same thing, just the difference is that, yeah, okay.
What?
He's caught it. He caught the vision. We caught it a while ago, actually. But you're right there. So, are y'all convinced then that 38 minutes is the answer to this? Even though we never came back to this form because the calculator doesn't work that way?
Yeah,
This is still time?
because we wanna find out what the temperature stays.
So why is that
That's the difference, it has to be 3.5
This time right here, and this one is dependent on this.
Okay.
Why wouldn't, plotting the t values and then fitting a curve to that and putting why wouldn't that work for right
It probably would.
It didn't, I got.
Well, you'd have to put that
Well,
8.5 on the other side.
did you get everyone close?
34.1.
If you change.
And then you add 4.5.
No, you don't add time to temperature together. This is a temperature. Yeah. But the time you got was 34 something, and then you don't add times to temperature.
No, you add the
If you add the
4.5 to the
4.5
equation, not the 30.
You have to move the.
And then
Oh!
you put it in.
Yes.
What?
If you took this 4.5 over here, added 4.5 to the end of this, so you had actual t right here, then figure in.
No, because I did it with the actual T, so I don't need the 4.5.
I'll just rewrite.
I graphed the.
It's gotta go somewhere.
News off cooling still requires a difference. So if you put that environmental temperature on the other side and add 4.5 over here, so the T equals all of this, then it probably will work. I'm trying to focus on the difference in the temperature. If you want to do it with just the static temperature or just the temperature list, then this initial temperature, this surrounding medium temperature's got to go over here. So that its actual T equals something, not T minus 4.5.
I'm confused.
You can't just get rid of 4.5.
It's just that
you move
you
it.
can't just get rid of it unless you're approaching zero, but then you've got ice and you can't stick the thermometer.
Am I pushing 0? Maybe I am.
Unless the thermometer was already in it.
So if I
Okay.
hit that,
Yeah, if you put the 4.5 into your equation, that's just a vertical shift up and that should adjust everything, I think. Okay? Are there any other discussion? Sam is exhausting, but he has to get something. Anything else? Because we're at the end of the section now, so now you got everything you need to do these exercises.
I think we're just gonna send it.
I say that didn't work either.
It didn't work to move the.
Jay, are you doing Moby Max?
Everything.
Moby Max.
I'm never touching.
Not Moby Max.
Alex.
Alec.
Yes, next period.
Moby Max is at the.
Next period is Alex.
That.
And just so you understand, this is just to keep the glare off of the screen. Yeah, okay, we haven't ended the stream yet. So.
Great.
So, that's, I was wondering if you were worried about safety.
I was.
So, we're done, Sonny.
Looking at it going, there must be something I don't know.
Yeah, I used to have it on the desk and the glare was so awful, you couldn't read what I'm talking
I'm taller
about. So now the glare's on. Okay, all right, yeah, you're welcome back next period.
It's not true. You have to say it was a lie.
Hey, Jay, I got 47.
It's closer.
You're right, but it's so much more fun walking than ever. You know?
Probably,
Why do they?
it has to do with adjusting for this E and the fact that this is not E. You're gonna have to do the conversion you're talking about, log B or whatever, to actually convert it to this before you add that 4.5 over. Because this is the calculator's exponential model, we have to use this.
I had to let it
Yeah.
down.
Because that's what's graphed,
But that's what the calculator's graphing. We're
Yeah.
it's based off of those plots.
right, based off of list 1 and list 3.
No, list 1 and list 2.
All I'm saying is, in order to use this, you're gonna have to convert that part of it to that.
I'm gonna have to. I'm not using that later.
You're just using this.
Yeah, so I've got, so I'll do the whole thing. So I've got this one and this.
Maybe I'll just go home.
I was about to no. Jose, how was that very much wrong? This one and this two.
Wait, hold up. 24
I got
through
that.
36 even, and 34, 35.
So I got that there.
Oh my gosh.
Not until you add
6 is
4.5.
more like this.
But we're just trying to find out. Because I mean, fell asleep.
My list two is.
Yes.
So are we just trying to find out what this is 0 or 8?
When this temperature is there.
Yeah.
So wouldn't that be what this graph is saying?
I approve.
You still haven't accounted for this difference. The fact that it's cooling at 4.5 and we'll never get any colder than that.
Number one.
You're letting it approach zero.
Use separation of variables to solve the initial.
Well, shouldn't just graphing that account for that?
No, that's completely against Newton's law of cooling.
No, because these should be approaching 1, right? Just that function.
Yeah.
So why would this graph only approach 4.5?
Sides.
Why does it go down as far as it does?
Because you haven't accounted for the 4.5 anymore.
This is just wide.
It can only approach this as this approaches zero. This is going to zero.
Cross. I know, so why are these approaching? So that's just the error in our fit, huh?
No, I don't think it's the error in your fit.
It's what, it's actual.
Yeah.
Exo
Because this should approach
That makes
4.5,
sense.
right?
I was like, this isn't gonna end up right.
Where have you ever accounted for 4.5 in anything that you've done?
This. Because this is the actual thing. It's going to 4.5, right?
Not unless you account for the difference. It's the difference that is exponential here. Not the temperature, it's the difference in temperature.
If they kept going with this data though, it should only get to 4.5, right? Or it shouldn't even get to that.
It shouldn't even get to that.
Yeah, so should this data match that, right?
Not necessarily,
Yeah.
because you haven't accounted for what it's cooling to, what it's approaching.
But they did, because they actually had it happening.
If you could see data clear down to there, yes, then you would have a different set of data and it would probably look different. But this is all you've got.
So why don't they make that match? So
If
if we add 4.5 to this, that's just like getting another number.
I don't know.
You use this y equals ab to the x, and this is your y value, this is what your temperature is. And this number right here is less than 1. This whole thing is gonna go to 0. Because this is going to
Right there. So did my stat, did it say it didn't plus anything?
No.
So it
It's just this.
So that's why we're supposed to do our regression off of what's 1 less 3.
Minus
Yeah.
So e both sides.
Wait, no, no.
Y equals e.
If I do that,
Half x squared. Is that it? I can sign it.
and now if I go to 3.5,
Well, how did you get that? I need to know where you guys got this.
then I should get the right.
Did you forget?
Right, because it's the difference, well, we use this
Oh, then
one
you have
next
to
time.
find
You do?
Yeah, you have to find out.
Or, what do they say? Read me the thing. Why?
No, you're right.
Yeah.
What is this?
What is it, what is y equals, y equals something, y equals what do you mean?
Are you sure you're all right?
What?
Oh, okay. So when
Difference
you have to.
between things that's exponential.
So because me off is that our calculator doesn't do this plus whatever.
Right,
And so it made a steeper curve to get down to 0.
right, because this part right here will go to 0.
Oh,
All right.
Sweet.
All right.
That's good. Nice.
Whatever it
I
is.
guarantee you.
So when you're doing the
I love my version.
here, are you not using
That's what I get for C.
this function? Okay, so how would I find this?
No, you should.
Yeah. 3 hours.
So, calculate.
You also have to put the other one in, because you have two variables.
We
A
should-
and y naught. You need the other one, so that you have to.
Yeah.
And then I will text me.
Yeah.
Where are you?
I would, but I don't have it.
C
equals
Where's my pencil?
9.
3.
I was about to say, isn't it in your hand? Then I was
5 hours.
Oh my gosh, yes.
Now, we decide.
Found C, but.
Simultaneously together. In other words, we have
I
to
probably
solve
should have
this
brought my
and
calculator.
replace
Is that
it.
my
calculator?
You grab my calculator. We'll do 19 on calculator.
You guys, right?
24 to 30 even.
So ask her, she asked me to
34.
So then there's nothing.
35.
Yeah.
41.
Obvious.
44.
These are
46.
the main way to go down.
44, 46.
That's a zero.
Yes. Finally, but okay, they don't fall on the line.
So 4 equals.
Plus, we don't push it back.
Indestructible.
Then you go back up to B.
That's
So it is
why don't we
okay.
just-
So we put it in this stuff, right?
C is
Put it in right here, for
the
example, put it in there.
So then we just
Yeah,
plus.
whatever that number is, we can divide it by that.
Where's the marker?
So E to the beta.
So then it'd just be plus.
Anyway,
Whatever.
Oh.
Well, it's really, you don't need to do it, right? And then
Whatever that number one is, you don't like.
But then you'd have to E
Oh,
that.
what do I do now?
So
They gave you
y
two snapshots, and you had to
equals
use them as a system.
E to the 1/2 x squared.
Oh, it's up there. Then eat everything. Would it be eat everything? If you eat everything, that's not. Eat everything. Because it's a constant. You can separate these two.